Hi all, this is Dr. K.G. Shanti, Professor, EC Department, R.M.K. College of Engineering and Technology. Now in this particular video, we are going to see what happens at the normal incidence at a plane dielectric boundary. That is, when a wave is incident on a plane dielectric boundary. Now reflection of a plane wave when it is normally incident at a plane dielectric boundary. Right, when a plane wave travels from one medium to a different medium, it is partially reflected and partially transmitted. Right, the proportion of the incident wave that is reflected or transmitted depends upon the constitutive parameters. When I say constitutive parameters, the permittivity epsilon, the permeability mu, and conductivity sigma. Suppose, let us assume that there is a plane wave propagating along z direction and is incident normally on the boundary z is equal to 0. I'll show you the diagram in the next slide. Let us assume that the first medium is a dielectric medium characterized by epsilon 1, mu 1 and sigma 1. And the second medium is a dielectric medium 2 characterized by epsilon 2, mu 2 and sigma 2. The boundary line is z is equal to 0. Medium 1 is at z less than 0 and medium 2 is at z greater than 0. Now look at the diagram. Now this line represents z is equal to 0. So the wave is incident. When I say normal, perpendicular to the boundary, right? Part of the wave is reflected back and part of the wave is transmitted. So the wave is propagating along the z direction. Right, now when we look into the diagram, we have the transcripts I, R and T. Right, I represents the incident wave, R represents the reflected wave and T represents the transmitted wave. Now z is equal to 0 is the region 1, z greater than 0 is region 2. Here the medium 1 is having the parameters epsilon 1, mu 1 and sigma 1, and medium 2 is having the parameters epsilon 2, mu 2 and sigma 2. And one more we have, when you look into it, you have a dot with a circle. It represents an arrow pointing perpendicularly out of the page. If I have a circle with a cross here, it means that an arrow pointing perpendicularly into the page, right? Dot with a circle out of the page. Cross represents a line into the page. Right, now as I told you in the previous slide, EI and HI is traveling along z direction in medium wave and it's the incident wave. As I told you, EI and HI is incident wave. When I say E, it is the electric field and H, it is the magnetic field. ER and HR represents the reflected wave traveling in AZ direction, because when they get reflected at the boundary, it will be in the opposite to Z direction and hence it is AZ direction. And ET and HT are the electric fields and magnetic fields of the traveling wave. They are traveling along AZ direction and in medium 2. Right, so now let us talk about what are the total fields in medium 1. The medium 1 comprises both incident and reflected wave, and hence E1 is going to be ER, incident wave plus reflected wave. And what is H1? H1 is once again reflected component of incident, that is incident magnetic field and reflected magnetic field. The sum of these two are the total magnetic field present in medium 1. Right, the total reflected wave combines with the incident wave to form a standing wave. Right, reflected wave, when it combines with the incident wave, the resulting wave is going to be a standing wave. Right, what happens in medium 2? Right, medium 2, the wave, that is the electric field components is E2, and E2 is nothing but equal to the transmitted component ET, and H2 is nothing but the transmitted component HT. right? The transmitted wave is a purely traveling wave, right? And hence there is no maxima or minima. Whereas in medium wave, the incident wave and reflected wave get overlapped and we have what is called as standing waves. Now we know the boundary conditions, right? The boundary conditions are going to be tangential component of electric field component is continuous at the boundary of a dielectric, what we have derived in the boundary conditions for electric field. In the same way, boundary conditions for magnetic field is tangential components at the boundary of medium 1 and medium 2 are continuous. That is H1 tan is equal to H2 tan. So at the interface at Z is equal to 0 between medium 1 and medium 2, what happens is EI plus ER is equal to ET. Now when I apply the boundary conditions, in the medium 1, the total electric field is EI plus ER. In medium 2, it is ET. So when they are continuous, we have EI plus ER is equal to ET and HI plus HR is equal to HT, right? And we all know the intrinsic impedance eta is equal to E by H, right? So if this is the condition, what will be EI? EI is nothing but the incident component of the electric field. So EI is equal to eta 1 into HI. Whereas look into the reflected component of electric field, you have minus eta. Why minus eta? Because the reflected component is opposite in direction to the incident component. So we have ER is equal to minus eta 1 into HR. So the reason is very clear here. Reflected wave is opposite to that of incident wave. Now we have EI is equal to eta 1 into HI, ER is equal to minus eta 1 into HR, and eta that is ET is equal to eta 2 into HT. Now as per the boundary conditions, that is magnetic field component is continuous at the boundary, right? In medium 1, what do we have in medium 1? HI plus HR is equal to HT, right? This is the magnetic field component in medium 1 and magnetic field component medium 2 is HT. Now what is HI? HI is going to be EI by eta 1 and HR is ER by eta 1. HT is ET by eta 2. So this represents medium 1 and this represents medium 2. Now what I am going to do is I combine that is 1 by eta 1 is taken as common. So I have EI minus ER and here 1 by eta 2 into EI plus ER. Okay, right. Now because I have replaced ET by EI plus ER. Now I collect the EI component separately and ER component separately. I take an LCM. Eta 2 minus eta 1 by eta 1 into eta 2. Here eta 2 plus eta 1 by eta 1 into eta 2. Now what I have? ER by EI is equal to eta 2 minus eta 1 by eta 2 plus eta 1, right? Now what I am going to do is this ratio of reflected electric field component to the incident electric field component is going to be called as reflection coefficient. So eta is equal to, that is this symbol, right? We call it as reflection coefficient. It is ER by EI, which is eta 2 minus eta 1 by eta 2 plus eta 1. Now ET by EI is equal to, ET you know, EI plus ER by EI. So EI by EI is 1 plus ER by EI. Now eta that is ET by EI is equal to 1 plus, you all know ER by EI is nothing but reflection coefficient, which is eta 2 minus eta 1 by eta 2 plus eta 1. Right, now I take an LCM. ET by EI is equal to 2 eta 2 by eta 2 plus eta 1. Now I am going to define a new term which is going to be called as transmission coefficient. What is transmission coefficient? It is nothing but the ratio of transmitted voltage wave amplitude. ET is the amplitude, right, of the transmitted wave to the amplitude of the incident wave. So eta is equal to ET by EI, which is equal to 2 eta 2 by eta 2 plus eta 1. Or ET is equal to tau into EI. right? 1 plus the reflection coefficient is nothing but the transmission coefficient. So 1 plus reflection coefficient, right, is nothing but 1 plus eta 2 minus eta 1 by eta 2 plus eta 1. When we take an LCM, we get 2 eta 2 by eta 2 plus eta 1. So this is going to be the transmission coefficient, and this symbol is going to be the reflection coefficient. Second important result is the maximum value reflection coefficient can have is 0 to 1. Right? And what is reflection coefficient? Reflected wave by incident wave. Right? So the magnitude of reflected wave will be for sure slightly less than incident wave. So that is why we say that it is going to lie between 0 and 1. Both reflection coefficient and transmission coefficients are dimensionless and complex in nature. Right? The equations are going to be reflection coefficient is ER by EI, and the transmission coefficient is going to be ET by EI.